Hi everyone, welcome to my channel. In this video we're going to go over some basic logic circuit design methods. So logic circuit design methods. So up to this point we've used Boolean algebra to describe a circuit's operation. We've used Boolean algebra to describe a circuit's operation, and we've also used Boolean algebra to simplify a Boolean expression. But now we're going to go over the basic methods used to design a logic circuit when the circuit output requirements are given. And the circuit requirements are usually given in the form of a truth table or as a word statement. So we're going to look at the basic procedures used to design a logic circuit when the desired circuit requirements are given. And the circuit requirements will be in the form of either a truth table or two and a word statement describing the outputs that we want for the given inputs. So before we get into the logic circuit design methods, there's two general forms of logic expressions that are used in these methods. And the first general form of expression is the sum of products. So sum of products expression, and we're going to abbreviate that S of P. And the second general form is called the product of sums, and we'll abbreviate that P of S. And then we'll look at examples of these two types of logic expressions. So here's some examples of sum of products expressions. And you can see here that the sum of product essentially is the sum of two or more terms, or each term is the product of one or more variables. So sum of product expressions consists of the sum of two or more terms where each term consists of the product of one or more variables. So the sum of two or more terms where each of these terms consists of the product of one or more variables. In this case we have this term here only has one variable. They can have two or three or as many variables as you want. But essentially this is the form that they take. It's the sum of products. The second general form of logic expression is the product of sums, or abbreviated P of S. And you can see here it consists of two or more terms in parentheses, and each term is the sum of one or more variables. So the product of the sums, P of S, consists of the product of two or more terms in parentheses, and each term is the sum of one or more variables. So with that background information, let's see how we can go about designing a simple logic circuit based on the output criteria, and that will be summarized in a truth table. So if we start off with a truth table with inputs A, B, and X, and we got 0, 0, 0, 1, 1, 0, 1, 1, and say we want an output that is high for this particular case and is low for these other three cases. So if we think about this, how can we get an output to be high for this particular case? Well, if we think about an AND gate is going to be high when both inputs are high. So how do we get an output to be high for this particular case and not for these other cases? Well, let's look at an AND gate. If we have an AND gate, and if we invert A, we put an inverter on A, this will give us a high output for this particular case and a 0 for the other cases. So it'll be high only for this particular case. So what we did is we inverted each variable that is 0. And in this case it's only 1, and that's A. So in order to use an AND gate, which an AND gate is defined that the output is high when both inputs are high and is 0 for all other cases. So all we have to do is guarantee that there is going to be two highs on the input of the AND gate, and we do that by just placing an inverter where we have the variable is 0. And we can do that for each of these four cases. So this here, what we need is we need A naught to equal 1. And B is equal to 1 in order to get a 1 out. So this here is A and B, and if A is 0, A naught is equal to 1. So this is A naught, and the output here, X, will equal to A naught B. So using just AND gates, we can develop, or we can produce, a high output for each of these cases by inverting the appropriate input variable. If it's 1, we leave it alone, and if it's 0, we put an inverter on it. So you can see here we can produce a logic level 1 for each of the four possible unique input conditions by just putting an inverter on the appropriate variable to invert it before it goes into the AND gate. And this, of course, is just a straight AND gate, and we already defined an AND gate as producing a 1 on the output when both inputs are 1. So this is just your basic AND gate, and for these other three cases here, we put an inverter on the variable that is 0. So we invert it before it gets to the AND gate. And this same technique can be applied to AND gates with more than two inputs. Now, what if the logic circuit needs to produce a high output for two different cases? So if we had a two-input circuit A, B, and X, and there were two input conditions that would produce a logic level 1. So what if there were two cases here instead of just one? Well, we can go ahead and write the expression or the AND term for each of the conditions where the output is 1. So here, based on what we've learned, this would be A naught B would be the expression for that case, and the expression for this case would be A B naught. And for each of these cases, either one or the other or both, we need to have an output of 1. Well, that sounds like an OR gate. So what we would do is we just have two AND gates. We have A, which has an A naught. This is A, B. And the output here is A naught, B. And here we have another AND gate. And this would be A, and this would be B. And the output from here would be A, B naught. And we just feed these two inputs into an OR gate. And the output here would be A naught, B, ORed together with A, B naught. And that's what the final output X would be equal to. And this is the Boolean expression for that output. So what we would do is you write the AND term for each case from the truth table where the output is a 1, and then you OR those AND terms. And then you end up with an expression which we've already defined is the sum of products. So here we have two terms, and they are the product of A and B, and we sum them together to produce the total output X. So this same method can be used for circuits with more than two inputs. So here we have a truth table that summarizes the outputs for each input combination. So we want an output X equal to 1 in this case, and this case. So the first thing we want to do is we want to write the AND term for each of these cases where the output is a 1, and each variable in the AND term will be either inverted or non-inverted depending on its value in the truth table. So here this expression is A naught, because A is 0, B, and C naught. The AND term for this case is going to be A naught, B, C, and the AND term for this case is A, B, C. So here we've created each AND term for each case in the table where the output X is going to be a 1. And then we know each of these terms, each of these AND terms will then be summed together with an OR gate. So the total output X is then going to equal to A naught, BC naught, or together with A naught, BC, or together with A, B, C. So to review, we have the truth table, which summarizes the output requirement for the circuit we want to design, and we create an AND term for each case where the output X is equal to 1, and each AND term contains each input variable in either inverted or non-inverted form. If it's a 0, it's inverted, in this case A naught, B, and here C is 0, so it's C naught. And then each AND term is then ORed together to produce the total Boolean expression for the output X. And each of these AND terms represents a 3-input AND gate in this case, and each of these outputs will be fed into an OR gate. And this is what the algebraic expression would look like with gates. So each of these terms represents an AND gate with the appropriate input inverted or non-inverted, and the outputs from each of these AND terms, 1, 2, and 3, feed this OR gate. But once we end up with a Boolean expression, we can apply the rules of Boolean algebra and the theorems usually to simplify this Boolean expression. So we end up with a logic circuit that will produce the same logic 1 value for each of these cases, but will use fewer logic gates. And we'll show that process next by defining the output of a logic circuit with a word statement defining the output, and then we'll develop the truth table and then the Boolean expression from that, simplify it, and then come up with the circuit. So say we want to design a logic circuit that has 3 inputs, A, B, and C, and whose output is high, or logic level 1, when a majority of the inputs are high, or logic level 1. So we have a circuit that has 3 inputs, and when the majority of the inputs is high, we want X, or the output, to be high. Let's look at the truth table for that based on this word statement. So here's the beginning of a truth table for a 3-input circuit, and we want the output to be high when a majority of the inputs is high. So that will occur here, and here, here, and here. And for all other cases, we want the output to be 0. So now we have to create an AND term for each case where the output is a 1. And so here we have A naught, B, C. Here we have A, B naught, C. Here we have A, B, C naught, and here we have A, B, and C. And the output X will equal to the sum of each of these AND terms. So we have A naught, B, C, or together with A, B naught, C, or together with A, B, C naught, or together with A, B, C. So here's the Boolean expression for the output X, and this can be simplified using Boolean theorems. So the Boolean theorem we're going to use to help us simplify this expression is the Boolean theorem that states if you OR X with X, it'll equal X. So you can add, in Boolean algebra, you can add another term that's identical and OR them together, and it's the same as X. So in this particular case, we have this term here, ABC, has 2 variables in common with each of these other terms. So we can add this term here multiple times to this expression without changing it. So one of the theorems we're going to use to help us simplify that expression is the theorem that states X ORed with X is equal to X. So we can take that last term and add it multiple times to that expression without changing the expression. So the original expression, we have X equal to A naught BC, or together with A B naught C, or together with A B C naught, or together with A B C. So we can double up this last term here, add multiples of that without changing this expression under the rules of Boolean algebra. So this last term has 2 variables in common with each of these other terms. So here we have X equal to A naught B C, or together with A B C, and then that's OR together with A B naught C, or together with A B, C, and that's OR together with A, B, C naught, OR together with A, B, C. And now what we can do is factor out x equal to, in this case it's A, so we take out the BC and we end up with A naught ORed with A. And in this case we have AC, and that's times B naught ORed with B. And in this case we have AB, so AB, and we have C naught ORed with C. And using the theorem that states that X ORed together, X ORed together with X naught, right? X ORed together with X naught is equal to 1. So each of these terms here goes to 1. This goes to 1, this goes to 1, and this goes to 1. So we end up with X equal to BC, OR together with AC, OR together with AB. And this expression here is equivalent to the original expression we derived from the truth table. So these two expressions are equivalent, and this is the simplified one, and this just is 3 two-input AND gates. So here we have inputs B and C, and here we have another two-input AND gate with inputs A and C, and here another AND gate with inputs A and B. And those feed a 3-input OR gate. And this will give us a value X will be high when a majority of these inputs are high. You'll get a high out based on this truth table. So with this method here, we've ended up producing a logic expression that's in the sum of products form. We can also use this same method to produce a logic expression that's in the product of sums form, which you end up with OR gates feeding an AND gate. And let's show how that, let's go take a look at that process. So we're just going to use the same circuit requirement, which is that we want to produce a high output when a majority of the inputs is high, except now instead of showing the AND terms for X, we're going to produce an AND term for each case for the opposite, X naught. So here would be X naught. So we just reverse, there'll be a reverse of X, and we're going to create an AND term for each case where X naught is 1. So here this is A naught, B naught, C naught, and here we have A naught, B naught, C. Here we have A naught, B, C naught. Here we have A, B naught, C naught. And those are the 4 AND terms for X naught. So let's write the expression, the Boolean expression, which is x naught is equal to a naught, b naught, c naught, or together with a naught, b naught, c, or together with a naught, b, c naught, or together with a, b naught, c naught. So now we have a Boolean expression for x naught, but we want a Boolean expression for x. So again, our next step is to try to start simplifying this expression. And we can use the same technique with the theorem that says that x ORed with x is equal to x, except in this case, this is the term here that has two variables in common with each of the other terms. So we double up on this term here. So I've already gone ahead and added this term and this term. So I've doubled up this term here and paired it up with those other two terms. So now we can start simplifying, find out what they have in common. This here is a naught, b naught, and that has c naught ORed with c. And here we have a naught, c naught, and together with b naught, b. And here we have b naught, c naught, and with a naught, a. And using the Boolean theorems, these go to 1. These are equal to 1. So we have x naught is equal to a naught, b naught, or together with a naught, c naught, or together with b naught, c naught. And the next thing we want to do is to get rid of this inversion sign. So we want to solve for x and not x naught. So we invert both sides, and that ends up giving us this equal to x. So now we have to break up this long inverter sign. And how do we do that? We use De Morgan's theorem. So here we can use De Morgan's theorem to start breaking up this long inverter sign. So we say use De Morgan's theorem. So to start breaking this up, this would be x equal to a naught, b naught, and that will be and together with a naught, c naught, and this here would be b naught, c naught, naught. And then we further break up these other inverter signs, and this will equal to a double naught, or together with b double naught, and this will be a double naught, or together with c double naught, or together with b double naught, c double naught. And double inversions just cancel each other out. So we end up with x equal to a or b, parentheses, and with a or c, and with b or c. So now we have x in the expression for x is now in the sum, is in the form of the product of sums. So here we have the product of sums, and each of these terms is the sum of the two input variables. And each of these terms is an OR gate, and the output of each of these OR gates feeds a 3-input AND gate. So this logic expression converted to a logic circuit will look like this. There'll be 3 OR gates with the appropriate inputs. So in this case we have A and B, and we have another OR gate here. And this is this term here. This is A and C, and another OR gate here. And this is B, C. And then these feed a 3-input AND gate to produce X. So these are the 2 equivalent circuits. One is in the form of the sum of products, where we have each term here is an AND term, and each AND term is then ORed together. And here is the equivalent circuit in the product of sums form, where each term is an OR gate, and each OR gate output feeds an AND gate. In this case, a 3-input AND gate. So those are the basic techniques or methods you use to design a logic circuit, either from information obtained from the truth table showing the desired output level for each possible input combination, or if it's presented to you in a word statement. In this case, we wanted a circuit that produced a high level or an output that was high when a majority of the inputs was high. And either of these 2 circuits will fit that criteria. These are equivalent, and they'll produce a logic level 1 when any of the majority of the inputs is 1. So if you found this video interesting, feel free to subscribe, like, and/or comment. And thanks for watching.